All right. So let's talk about this a little bit. One of the things I was looking at very particularly was number 21. Okay, number 21 should have looked very much like number 19 yesterday. That is a very kind of fundamental type problem that we need to be able to work through and show that work and all those good things. Now, I haven't decided whether I put that problem. I tell you, there's going to be a problem like that where we've got to go through and do that, like number 21, with the max, min, increasing, decreasing, number line, that stuff. I don't know if I'm going to put it on the calculator or the no calculator, but I will tell you this, it doesn't matter. If I've got it on the calculator or the no calculator, your work will be almost identical. All right, and we'll talk about that when we get to that problem. Now, we've got a quiz coming up on Tuesday. Quite honestly, the quiz could probably be Monday. I don't like to have a quiz on Monday if we don't have to. But there is enough new stuff we're going to hit today that it probably will not hurt to go over some things again on Monday. All right? But there won't be, then on Monday, we may go into some new stuff. I may give you some time to just review. I don't know exactly how Monday will look for sure. We'll definitely spend some time reviewing. But there won't be a set of exercises then to review. You know, last quiz we kind of did, but sometimes we do, sometimes we don't. This is really the review. I mean, what we're doing right now, we're doing a variety of these different things. There are a lot of different things, like we talked about yesterday, that we're doing. They're all interconnected and related, but as you're doing them, they feel very different. The calculator worksheet problems seem very different than number 21, for example, which seemed different than that 13 or that other section of 3 through 12. And then doing the derivative the long way, you get into that algebra and all that stuff. And so they seem very different, even though we're really trying hard. I'm trying really hard to make the connections, and so you see and understand those concepts. So you really need to be understanding it as you go along and asking those questions and doing them. It's not one of those quizzes, I think I said this yesterday, it's not one of those quizzes you're going to be able to Monday night just sit down and study for. I mean, it's probably still a good idea to try to do that and go back through your notes and do those things. But it needs to be more a matter of just kind of, quick reviewing those things. Hopefully we went through it all and you can do those things as we go. All right, so that's kind of, we're going to try to do some of that today, and we're going to try to do some of that tomorrow, or Monday, excuse me, as we review through this stuff. So let's start with number 3 through 12 here, and we've got the picture. Now, I apologize, those of you watching the video, we're looking at the picture on page 120 for problems 3 through 12, and we'll bounce back and forth. So we've got to recognize. And on the board here, I've got big F. We talked about big F, and we've got to understand this connection. The big F is the same as the derivative of big F is big F prime, but that's the same as little f. And big F double prime would be the same as little f prime, and so forth and so on. So we've got to understand the notation. So once we understand that, then these problems should hopefully be pretty easy. So like on number 3, what's the slope of big F at 4? Well, my hope is that you would immediately, when you hear that, you would write that on your paper. I mean, let the notation be your friend. For some of you, you're letting the notation be your enemy, right? The notation, if you understand it and will write it, it will tell you what to do. Okay, so some of you are overthinking it. If it says find the slope of f at 4, to me, you write that down, and then you look over here on the chalkboard and you say, oh, big F prime, that's the same as little f. So big F prime of 4 is the same as finding little f of 4. And since this is the little f graph right here, then all we need to do is find that y value at 4, and that happens to be 5. And so therefore, the answer to this question is 5. Okay, so let the notation help you. The notation can literally tell you what it is you need to do. All right, so let me move through some of these. You can ask about these. Well, they're quick. We can tell the answers. Where is big F increasing? Number 4. The whole thing, 0 to 10, because little f is always positive. Number 5, where does big F have an inflection point? Well, that's when, if we think of the chart over here on the board, when big F changes concavity would be when little f changes positive, no, increasing to decreasing, right? So little f has to change from increasing to decreasing. Well, this graph changes from increasing to decreasing at its max and its min. So it's at 1.18 and what was the other point? 8.19, right? So big F has points of inflection when it changes concavity. Little f at those points changes from increasing to decreasing or vice versa. It said justify your answer, so you would need to say that. Same thing with local max min. We talked about that on number 19 and number 21. You have to, when you do a local max min, you have to justify that answer. Here, the reason it's inflection point is because little f changes from increasing to decreasing. How many roots does little f have? Well, that would be where big F has a local max, a local min, or a flat spot. Okay? And that would be at those same 2 points at the, oh wait, I read the wrong problem. That was dumb. I was reading number 14. Where is big F concave down? That's when little f is, no, where little f is decreasing, right? So big F would be concave down when little f is decreasing and when little f prime is negative, right? So big F's concave down when little f's decreasing. So that'd be from 1.18 to 8.19 or whatever those numbers were there. Okay, from the peak down to the other one. That's where little f would be decreasing. All right, next one, number 7, F double prime of 5. Again, use your notation. F double prime of 5 is the same as little f prime of 5. So that means on the little f graph, you'd want to draw in your tangent line and estimate your slope right there. It's like -1.5 or something like that, something in that vicinity. Okay? Explain why f double prime has its minimum value at 4.67. Well, that's this point right here, 4.67. What is that point? That's the inflection point. Why is that the minimum? Well, that's where the slope is the most negative, right? When it says that f double prime has its minimum value, f double prime would be the same as little f prime. Little f prime is the slopes of this graph. So when are the slopes a minimum? It's when they're the most negative. That would be the lowest value, the most negative. Okay? And that's what happens right there at that inflection point, when they're the steepest going down. All right? Stop me if you've got any questions. All right, very quickly here, number 9. Oh, yeah, okay, well, actually not quickly. These last 3 are the ones we really need to work on. Okay? So, number 9 says, find the equation of the tangent line. Well, anytime we hear that, we want to do this right here. Okay? Getting ahead of myself here. Come on. All right, we want to do this. Now, we need a point, which they already told us f of 0 is 10, and we need the slope. So that'd be big F prime of 0. Well, what's big F prime of 0? Why? Because big F prime is the same as little f. So big F prime of 0 is the same as little f of 0. So we just read that right off the graph. So that is 7, put in the 0, put in the 10, and away you go. Okay? This was my favorite question of the whole thing. Number 10, does L, the tangent line, lie above the curve at 1? Somebody want to tell us the answer to that? No. Why? Concave up. Where in the world are you getting concave up? Oh, let's look. Here's some tangent lines right here. Which ones are above the curve? These over here. Where is the tangent line above the curve? Tangent lines are above the curve when the graph is concave down. So this question said, where is L above the curve, was really like asking, when is F concave down? Well, that's when little f is decreasing, right? When little f is decreasing. So you go to 1 and you look, Is little f decreasing at 1? No. The little f graph is going up at 1. And we look at that right here. At 1, this graph is still going up. Little f is going up. So big F would be concave up. Okay? So sometimes on those questions, you have to go several levels through it, you know. Where is L above the curve means where is F concave down. That's kind of a new one. So that's an interesting one. So that's good if you were able to think your way through that. Now, 11 and 12 are speed limit law situations. We know that big F of 0 is 10. They want us to answer if big F of 5 can equal 5. What I told you with speed limit law is you should draw and plot your points. So here's 10. So could we go over 5 and be right down here? Could the big F graph have that value right there? No. If it's going to, it has to go down. What do we know about these slopes? What do we know about little f? Whoa. Little f is positive, which tells us big F is increasing. Since little f is always positive that whole time, big F is always going up, so there's no way it can go down. So we know that for sure. Okay, then what about number 12? Could it be 15? No, it cannot be 15. Carly, why not?
What do you use this to do all the
So you actually picked some numbers off there. Where did you get those numbers that you're talking about?
I used that out of 5 is greater than 3.5.
Okay? Remember, yeah, in speed limit law, we need to know something about the slope. So right here, at 5, what is this y value? 3.5. And before that, it's even more than that, right? So the least big F can go up is if it goes over 5, what? 5 times 3.5? What's that, 17.5 or something like that? Is that where you got that number? I'll bet that's where you got that number. So if this is 3.5 right here, let's pretend that little f was 3.5 the whole time. Remember, that's the slope. So if you go over 5, you'd have to run 27.5, right? Now, you would not have to get that specific on this. You could just say, let me go back to, getting confused between all these things here. To be at 15, you would have to go up 5 and up, or excuse me, over 5 and up 5. What is that? Slope of 1. So to be able to hit 15, you would have to have a slope of 1. Little f is the slope. So you go back to this picture. Is the slope 1? No, it's way bigger than 1 the whole time. So since it's bigger than 1 the whole time, if you go over 5, it's got to go up more than 5. And that'd be good in that fraction, if you explained that. But if you go back to our last quiz, I think I told you that f prime was between -1 and 1. And you had to tell the speed limit law. Well, that's kind of what that graph says, that little f graph. It tells you it's from 3.5 up to like 8. So it's definitely got to be more than 15. All right, so those are some good problems. Those just take advantage of this big F, so there might be some of that on there. Those should be nice, easy problems because those are kind of like we did last chapter, and we did really good on that chapter. I haven't decided if I'm going to put some of those on there because there's just a lot of stuff on this quiz, and I want to make sure we can do it in a one-block time period. But like I told you earlier, this quiz may be one of those that is a little bit of a time crunch, so you'll have to be prepared for that. I want to save 21 for a little bit, so let's take a look at your calculators. And we're kind of purposely jumping around here a little bit because we do have a lot of different things going on, and I want us to be able to tie them all together here. And so I want to be able to bounce around a little bit here. So let's look at the worksheet. All right, there's a couple of them on the worksheet I wanted to do. All right, I wanted to talk about a couple different ones. So let's take a look at number 5. So let's type that one in. We'd have cosine of x minus 1. Is that, no, that's not right. No, oh, the minus 1's outside. Okay. Over x. All right? And then we go to our table, Control T, give us our table. My table's not really set up right now, so I'll go to my menu, go to my table settings. Make sure you can all do this. You want to start it at 0. And I would say 3 zeros is pretty good. 0, 0, 0, 1. Okay, I want to arrow up a couple. All right, and like I was telling you yesterday, I want you, when you draw your table, to not use this E notation. On the AP test, they say calculator syntax is not what you want to use. You want to use actual mathematical syntax. So when I draw my table here for this one, I want to see this first entry would be negative 0.0001. I think it was 10 to the negative 4. And then this was, what was it? So that'd be was it negative or positive? Positive. Oh, it'd be 4 zeros and a 5. And then this one was 0 and then said undefined. Okay, and then this one was positive 0.001 and this was negative 0.0005. I'm not going to get real picky. If you leave off a 0 or something there, that's not going to be the end of the world. And then this was 0, 0, 0, 3 zeros and a 1. Okay, so I want to see that on your paper. Now, if I give you one on the quiz and say, use your calculator, justify this is what I want to see. But I want everybody to understand, this question came up in the other class. Somebody asked, is the limit only exist on the ones where it says undefined right here? No. And so then my question to them was, does it even matter what is in this row right here? And the answer is no. That's the diner, right? I want you to make these connections now, these limit problems. That is what's going on at the diner. We said it doesn't matter. It's, do the two cars meet? You got a car coming in towards 0 here and a car coming in towards 0 here, and where do they meet? And so what matters is these numbers here. Now one's positive, one's negative, but where are they meeting? At 0, right? What you have is you got one car coming in from above the x-axis, one below, and they're meeting right there at 0. You can go to 3 decimal places and see 0. It doesn't matter if the diner's there, or it burned down, and they build it somewhere else. It doesn't matter. They meet. The only way the limit doesn't exist is if this number up here and this number here do not go to the same place or do not go to a number. Now, there was one where they were really big, like infinity, right? Wasn't there one where you were getting huge numbers? Like 33333 or something like that? That would be a limit does not exist one. What number was it? 6. Yeah, that would be a limit does not exist. And I think, didn't 10 do that? Or no? No, 10. Oh, 10 doesn't exist because the left was like negative 1/2, and then the other one was positive 1/2. Yeah, and so what you have is their cars are coming in, and they're coming in at 2 different places. One is negative 0.5, one is positive 0.5, so they're not meeting. So but again, where this is right here, the red row, right at as x approaches 0 or 3 or whatever, that doesn't matter. What's there does not matter. Okay, if it's undefined, it means there's a hole or maybe there's an asymptote or something. Okay, and so 6 would be does not exist, and so would 10. Okay, because if it's just going to infinity, then the cars aren't meeting there either. So that's does not exist. All right, now, let's go back to, there's another one I wanted to do then. Number 8. Okay, so let's go to that one. It's really important that not only we can see this, it's important that we can not only get on your calculator and do this, but quite honestly, once you do a couple, it's not that big a deal. I mean, you just keep doing the same thing, keep putting them in. You really need to understand what it is you're seeing here. So when I do square root Now remember, absolute value, you can't use the vertical bar. You got to go over here by the 9 and use this template right here. Okay, and there's absolute value right there. Okay, that's how you get absolute value. And then it's x subtract 2. All right, now my table is still set up. Now, once again, so your answer on this one was what? 1.414. Now, does this row matter? No. Now, this happens to be there, the diner was there, but it doesn't matter. It's these two right here. The cars are coming in, and they're both there at 1.414. But think about this one. If this would have been the algebra worksheet, remember the algebra worksheet yesterday? What's the first thing we do when we're not using our calculator on the limit problem? We plug it in. We substitute. So on this one, everybody do that on this one. Plug in a 0 on number 8. You get 0 take away 2, which is negative 2. The bars make it positive 2, and then you do the square root of 2. So that if you were doing this on a no calculator, we could. Square root of 2, that's 1.414. So the answer is square root of 2. Remember what we said? If you plug in and you get a number, what do? You stop. You're done. That's your limit. That's your answer. And that's what's happening here. If you look at it on the graph, everybody, I want you to notice what's happening here. What we're saying is the cars are meeting right there. 1.414. Now, there's no hole there. This one doesn't say undefined, but we don't even care. If there is a hole, the cars still meet. If there's not a hole, the cars still meet, right? So that's what's going on when you see that number in there. And that was throwing some people off. Okay, now, one more that I wanted to do. Now, we don't get to see it quite as good as we used to get to see it, and that's the new operating system here on this calculator. They've kind of fixed it. But let's put in number 7. Let's put in number 7. All right. Now, so we got parenthesis 1 plus x. I like talking about this one because there's some cool stuff going on with this one. Raised to the fraction 1 over x. This is a really cool function. Number one, look at the graph. I mean, it's got all kinds of crazy stuff going on. But we're only looking at when x gets close to 0. Now, here's why I say this one was a little more interesting before. The calculator used to put a 1 right here instead of undefined. There used to be a 1 there, which really got confusing for people. Let's pretend there is a 1 there. What do you put for your limit answer? What if there was a 1 right there on this row and we're doing x approaches 0? What's the limit? We have an answer of 1. So what is it? The answer is 2.718, right? What have I been showing up here? Do we care about this row? We don't care what's there. This would be an example of the diner moving, right? The cars are coming in where? At 2.718. At the spot, the dot's at 1. That would be an example of the graph that looked like this, that comes up like this, the dot's at 2.718, or the graph, but then the actual output value would be down there at 1. The limit is up here, where the cars meet. See, I want you to see that connection. When you look at this table, I want you to be able to compare that to this. Now, it was actually a mistake. It shouldn't have been a 1 there. But as far as limits go, it doesn't matter that it put a 1 there. Okay? The limit is 2.718. Now, by the way, what's 2.718? E. 2.718 is E. Okay? You're 0 for 2. You better quit volunteering. Okay? 2.718 is E. Now, where in the world, why does that come in? Well, this is really kind of a cool function. I'm going crazy. I'm so excited about this problem. Okay, look at this. 1 plus x to the 1 over x. Now what we have is x getting close to 0. Now this is something we're going to investigate a lot more later. Okay, when we start getting into infinity. Infinity is kind of a crazy thing. But as x is getting close to 0, what's happening? Well, what's happening inside the parentheses? As x gets really close to 0. It's getting really close to 1. But not quite 1, but getting close. And what's happening to this as x gets close to 0? Well, undefined, but, okay, you redeemed yourself. Getting really big, right? As x gets close to 0, this fraction's getting really big, like towards infinity. Now, what's 1 to infinity? Well, you can see why the old version of the calculator put a 1 there, because we all learned that 1 raised to any power is 1, right? However, is this really a 1 in here? No, it's just getting close to 1. So what's happening is you have a base that's becoming 1, which when you raise that to a power should be getting close to 1, right? 1 raised to a number should be 1. But you've got a power that's getting bigger, which normally makes a number get bigger, right? So if you've got a number that's not 1, and you raise it to a power, it's like 1.01 or 1.02 or whatever, and you raise that to a really high power, that should be getting bigger. So you've got two competing forces happening here. You've got the power going to infinity, which is trying to make the number bigger, and you've got the 1, which is trying to make the number be 1. And those two are kind of fighting it out. Now what's happening is it's not really at 1, and it's not really up here, and it's kind of, they come together, and guess where they come together? At E. At E, of all places, 2.718, which is another reason people say, what's the big deal about this number E? Well, we already saw one thing, e to the x graph is the only graph that its slopes are its y values. The slopes are its y values. It's its own derivative. Here we just saw another cool place that e pops up in this scenario. Okay? So there's a lot of those kinds of things. That's why I kind of like this problem. But for what you guys need to know about this, it doesn't matter what this row is. What are the two cars approaching? They're approaching 2.718. That is the limit. This, what's happening is you're getting negative powers. And when you have negative powers, you get like 1 over stuff. And not only that, but you get, like, let's say x is a negative 2. So now what you get is negative 1/2. And so when you do that, that's like 1 over a 1/2 power. But that means square root. And then 1 plus x, when x gets negative over here, there's going to be a negative in there, so it's going to be undefined. So there's going to be a whole bunch of places where this is undefined. So it's just crazy. There's little pieces where it's defined, then it's undefined, then it's bouncing around. And so, and notice it's kind of between -1 and 1. And it's, yeah, it's just a bizarre number. And so it's not anything, and plus the calculator has limitations because the calculator will plot a point and graph it, and they'll plot another to connect them. And sometimes there aren't really points in between there, it's just trying to connect them. So we can't tell much there. We'd have to zoom in, but it gets kind of crazy. All right. So let's move away from that then. We're going to come back to this idea though again. Like I said, we want to keep tying these things together. We want to make sure we can do them, right? Understand them. If we really do understand the concepts, we should be able to do that. Let's talk about 21. Let's talk about 21. You've got this function. What was it? 7. Yeah, g of w plus 63. All right. So this is, now, let's talk about this as if we could use our calculator, as opposed to not use our calculators, okay? Now, there are just very few differences. Now, I've decided where I'm going to put it, and the only reason I haven't decided where I'm going to put it is I'm going to try to make the calculator and the no calculator part about the same length. Now, remember what I told you earlier this year is that just because the problem says you can use your calculator doesn't mean you will use your calculator, okay? So I may take a problem or several problems where you don't need the calculator at all, and I'll put it on the calculator part. And partly I'm just trying to balance out those parts. Okay, I could have done that on the last quiz too, I suppose. Okay, but I just kind of added those calculator problems at the beginning on that other one. So I'm going to try to balance that a little bit. So let's talk about why those would be the same. So they ask, where's G increasing? Where's it decreasing? Where's the local max? Where's the local min? Well, somebody might say, well, I can use my calculator. I'll just graph that and see where they are. No. You will get no points for that. You'll get no points for that. Okay? If you put down those answers just by looking at a graph of G, you'll get no points. Okay? That's the way the AP test works, and that's the way we're going to do it. So what do we say you have to start here? Which is good, because none of you guys did that, it looks like. So that's good. So we do G prime. So we do the derivative at 63w to the 8th minus. Now, that might be one you say, you mean I have to do 18 times 7 without a calculator? Well, you already be a calculator student. I think you can do 18 times 7 without a calculator. All right, then what do we do? Make sure you do that. That is really key. Equals 0. You've got to set that up because we're going to find stationary points. Where does a derivative equal 0? All right, we can factor out a 63w to the 6. You don't have to factor out the 63. Now, here's where it could change a little bit if you have the calculator. If you want, you could go on and solve this on your calculator screen. You could type solve, and you could do this. Now, it might not be a bad idea if you have the calculator to do that, because my guess is some of you missed the plus or minus on this. I was kind of peeking as I looked around, as I was going around, and it looked like maybe a few of you did. Because now we set each of these equal to 0. Well, this one would be w equals 0. And this one would be w squared equals 2, w equals plus or minus square root of 2. So if you did not have the minus square root of 2, see, now you're going to be off. So if this was a calculator one, you could have went over here to your calculator and you could have said algebra, solve, and you could have typed in 63 w to the, what was it? 8th. W to the 8th, oops, minus 126 w to the 6th equals 0, comma, w, hit enter, and you get all the 3 answers. Okay? So, very few differences in how you have to show your work. Calculator or no calculator, this would be one of the differences. So you could come over here, so this line wouldn't have to be here, and you could have just had your answers. That would have been acceptable, but you have to have your derivative, set it equal to 0. Now what do we do? Number line. Number line. Be sure and label it G prime. Negative radical 2, 0, radical 2. Now you need this even if you're using your calculator. Now what someone asked me one time, I've never seen very many people do this, but somebody asked me one time, if I'm using my calculator, could I graph G prime and then just write it down? So let's say G prime did this, and then just use that as my negative, positive thing. Absolutely. That would be fine. I mean, if you want to graph G prime, draw a little sketch of it, and use that to show your plus minus, that's fine. Okay? Because it's really the same thing. I don't know if that's what that looks like, but you could do that. But I think the number line is probably just about as fast. Okay? Now, negative root 2, we got to know that that's about negative 1.4. So what would be a number over here? Negative 2, negative 1, 1, 0. Another comment I always like to make when we get to this point. When I make my number lines, I use hash marks or tick marks right here for those 3 stationary points. I would not put hash marks or tick marks for these numbers, because then it just gets confusing where your intervals are. We have 4 intervals here. Say that again. Oh, yeah, I'm sorry. Yeah, that's 2. So I would just put your 3 hash marks here for your stationary points, and then here's your 4 intervals in between. Now, another thing. So now let's imagine this is no calculator at this point. If it's calculator, it's easy to plug in. But you really don't even have to take that much time. I mean, if we're talking about this quiz being kind of a time crunch thing, maybe you look where you could save some time. when we plug in this negative 2, we don't have to take it to the 6th power. Because all we care about is what? Positive or negative. That's all we care about. So when I put a negative 2 into the 6th power, that's going to be positive. So I put negative 2 in here and square it. That's 4. 4 take away 2. That's positive. Matter of fact, I don't even have to worry about this 6th power at all because it's always positive. So I probably wouldn't even have to plug into it at all. Negative 1. Again, 6th power is positive. Negative 1 squared is 1. 1 take away 2. Negative. Put a 1 in. Again, negative. Put a 2 in. Positive. And there we go. So, what's happening? Well, what did it say? Where's the graph increasing? G. From negative infinity to negative root 2. And from root 2 to infinity. Decreasing from negative root 2 to root 2. Local max is where? Negative root 2. Because, and this is where you've got to write this, you've got to say because G prime is changing from positive to negative. And local min is here because G prime is changing from negative to positive. You've got to have that. And what's going on at 0? Flat spot. I feel like you guys got this down so good I don't even need to go over it. But that's what's going on. I'm going to give you a chance to practice one more of these. For sure, you're going to do one of these next week. Guaranteed. You're going to have to do this thing with number line, derivative, using your power rule, stuff like that. All right. Let's talk about a couple of new things. Well, no, I tell you what. Let's do this first. A little bit of practice, a little bit of review. Let's do something where you guys have to do some work, and it connects some of the things that we've been talking about. So, let's do this right here. F of x equals this. Find f prime of 4 by the definition of f prime. Okay, let's start with this. Find f prime of 4 by the definition. Now, if you want to help each other out, ask questions, that's fine. By the definition, which would be the quote unquote long one, right? That is not by the definition. The long one. I'm not going to say on the quiz, I'm not going to say the long one. I'm going to say by the definition. by the definition. Now, if we want to do the shortcut, and I'm not going to use the word shortcut either, what would we say? What's the shortcut called? The power rule, right? For a problem like this, the shortcut would be the power rule. What would be the derivative by the power rule? 2x subtract 2, right? But then you want f prime minus of 4, so you put a 4 into 2x minus 2, you get 6. 8 minus 2 is 6. So certainly on the quiz, since we already know the power rule, you'll know what your answer should come out to be, right? You'll know that you should be getting a 6, right? So that would be nice to know. But the grade will be based on showing the definition, obviously. So this would be one of those great examples of having the right answer may not get you any points. Okay. All right, so go ahead and finish if you're finishing up here. I've got the first part set up here. And, you know, this is the first thing we learned in section 1 of chapter 2. First thing we learned. And so is writing this out. So this is something you're going to have to do at some point, some way, shape, or form. Now, we learned 2 different versions of this. One is if we're finding f prime of 4, which is a slope at 4. But we also did ones where we were just doing f prime of x, right? So we'd have an x here instead of the 4 as we go through it. But it would look very much the same. In that case, we'd come out with just 2x minus 2 as our answer. Okay, so right here, we take and we let f of 4 plus h means plug a 4 plus h in for x. So 4 plus h there, 4 plus h there, that's what I've got there. And then we plug a 4 in, that'd be 16 minus 8, which is 8. We FOIL this all out, which is what I have right here. 16, take away 8 makes 0. 8h, take away 2h is 6h. We can factor out an h. We can cancel. Now we can put a 0 in for h, and voila, we get 6. Okay? So, that's good practice for next week. And we want to be able to do that. Now, let's connect that to something we've been doing recently. Let's connect that to what we did on today's worksheet with our calculator. Okay? Now, so let's go to this. So now the question is this one right here. Let's say f of x equals cosine of x. And we want to find f prime of 4 by the definition. So, get that started. Get it started. Which should be the same start that you had on the last one. Now, once you get it started, before you get too excited, be careful of trying to do some algebra that you cannot do. It looks like you should be able to do, but you can't. Somebody want to read to me what they have that they got started? Bree Miller, you got something started? Okay, what about the next step? Okay, so she's got the f of 4. I didn't even write that down this time, which is I almost always do, but I didn't this time. F of 4, limit as h approaches 0, f of 4 plus h minus f of 4 all over 8. Somebody got the next version after that then. Cosine of 4 plus h minus cosine of 4 all over h. Right? So we get that. Now, what's the algebra I was warning you about? You cannot distribute cosine there, okay? Because this does not mean cosine times 4 plus 8. So that's not a distributive, okay? So you cannot do that. Now, there is a trig identity for how to do cosine of A plus B and to expand it, but we're not going to get into that right now. So, there is no algebra we can do. Now, here's the connection I want you to make to the worksheets we've been doing. Yesterday's worksheet was algebra. It looked like this problem. Okay? Where we got a limit, and we did a bunch of algebra to it, some things canceled, we got our answer. Today's worksheet, we had a limit like this, but there was no algebra we could do, so what did you do on today's worksheet? What did you plug into your calculator? Tell me on this limit right here, what you would plug into your calculator. Let me pull up that worksheet. What did you plug into your calculator on this problem right here, number 2? You plugged in this whole mess, everything but the limit piece, right? And you looked at what was happening as x got close to 0. Now look at this one from your worksheet today. And now look at what we have set up right here. Aren't those the same thing? What's the only difference? Well, yeah, there's a cosine, but what else? There's h there instead of x. But couldn't we take this blue thing and put that into our calculator? Absolutely. We want to know the limit of this as h approaches 0. Now, up until today, the only time we've done that on these derivative definition ones, we've used algebra. We've done algebra to get them. But as we've seen now in our worksheets, we can do calculators to get them too. And on this one, there's no algebra to do, so guess what? We're going to go to our calculator. So everybody get your calculators out, and let's plug this in, except we can't use h. What do we got to do? If we're going to put it into our calculator and graph it, we've got to do x. Now, there's a lot going on here that I want to make sure everybody's understanding. So let's go ahead and do it. And let's see if okay, so we're going to have our fraction, and what is it? Cosine of 4 plus x. That's going to be really easy to put h instead, so we got to be careful. Cosine of 4, and on the bottom is x. And we hit enter. Okay, and my table is still set up. And so what do we have for our answer? 0.757. If you rounded, you can leave it 0.756. That's okay, right? We don't care about this undefined, right? See what we're doing? 0.756. Let's come back to this. Let's come back to this. And so we'll skip all that algebra stuff. And we got 0.756. Now let's see if we can put all this together here, what we've just done. Yes?
Is it okay not showing?
Oh. Now, okay, thank you. My directions on this problem would have been this. If this, and so this could be something I ask you to do on the calculator one. Remember I said you're going to have to do some table thing like this worksheet? I might just give you a limit like we did there and say use your calculator. Or I might do it in a problem like this. And so I might give you this, and I might say find f prime of 4 using the definition. Well, I'd probably do something like this. Set up the limit using the definition for f prime of 4. Then justify your answer by using a calculator table. You see what I'm saying? So what I would want you to do on this problem, if those were my directions, is you would then write out your table. Just like you did on the worksheet. Just like you did on the worksheet. But I would make that clear in the thing. But I want you to understand why you did that worksheet, to do those limits. Because now we're going to bring it back to these special kind of limits we have, which are the derivative. That worksheet you had today was just a bunch of different limit problems that were interesting. But now we're going to focus back on these limit problems that actually mean derivative. Now let's talk about 0.756. Because this number right here has two different meanings in this problem. Right? Numbers have different meanings. Like the number 100, for example. That could stand for how much money I have in my pocket right now. But it could. It could also stand for the score that you're going to get on the quiz next Tuesday. Right? There you go. It could have different meanings. So the number 100 could mean two different things, or multiple different things. So this number right here, 0.756, in this problem, it means two different things. What's one of the things it means? The slope of what? Of that function. Now, and it's really important that you say of what? Because I have two different functions here. Because did we just graph cosine right now? We graphed this mess, right? We graphed this thing. So that's a function of its own. But you're right, 0.756, one meaning is that this number here is the slope of the cosine graph at 4. And so if we did a quick cosine graph, it goes up, comes down like this right here. This is pi, which would be 3.14. This is 3 pi halves, which is like 4.7 something. So 4 would be right in here somewhere. So it seems reasonable that that slope would be about 0.7 something. Okay, seems reasonable. But also, 0.756 is what? Where the cars are meeting on this graph as h approaches, or x approaches 0. The cars are meeting at about 0.756 for this blue function back on this page. It's really important that you understand that. So this function has y values that are meeting at 0.756 as x gets close to 0. But this number also then is the slope, because that's what this represents, is the slope of the f function. Okay, tying that all together, very critical part of this. So we got the algebra way of doing limits, like the worksheet yesterday. We got the calculator way of doing limits. And now, important to understand that some limits mean something different. They mean a derivative, okay, if we have them set up that way. All right, let's do a couple of new things we need to put into our notes. We're almost there. We're almost done. Thanks for hanging in there on a Friday. And then I'll let you work and talk about what our assignment is. We're going to finish the back part of that worksheet, and we're going to have a few things in the book to just kind of review some things. But there are a couple quick new things we have to talk about. First of all, big F, we said, was antiderivative. Now, this one, in the grand scheme of things right now, is probably not nearly as important for the quiz. I haven't decided if I'm going to put any of these even on here. It'll be on our next quiz, I know for sure. But what we talked about is this. We said, okay, if we have big F, let's say big F, well, let's don't even call it big F. Let's just say the derivative of x to the 5th. What is that? Derivative of x to the 5th is 5x to the 4th. Okay? Now, yesterday we were talking about antiderivative, meaning going back. Okay? Now, let me write something down. You don't have to write this down right now. It's not important. But the power rule basically says n times x to the n minus 1. It says multiply by the power, then decrease power by 1, right? That's what the power rule basically says. Okay, now, let's say we had to go backwards. So let's say we started with the function f, 5x to the 4th, and we wanted to write big F, the antiderivative. Now, we all know it's what? X to the 5th, right? We just saw it right here. So if we go backwards and do the antiderivative, we know the antiderivative 5x for x equals. And Kelsey said something yesterday that made a lot of sense. If you're going backwards, you know the power's got to get bigger, right? But then what about this number in front? How do you figure out what that is? Well, it's kind of a guess and check. Well, actually, we could just take our power ruler, right? And we could just do it backwards. Yeah. Instead of multiplying by the power, then decrease power by 1, let's just go backwards. Let's increase the power by 1 and then divide by that power. So we would take 5x to the 4th, we would raise the power up 1, and we would divide by that new power. Sure enough, the 5's would cancel, and we would have x to the 5th. So we raise it up and divide by that new power. So the way that looks is to go backwards, it would look like this. That'd be your backwards power, right? That'd be your antiderivative in reverse. Raise the power up 1, and then divide by that new power. And that's how you can get an antiderivative, how you can go backwards. Yes. And you would need, anytime you do an antiderivative, there would then be a plus c tacked on to it as well, right? But we're not going to spend much time on that. We could, there's no reason we couldn't, but there's so many things we got going on right now that's just one that I'll probably save for the next quiz when we do some more of these derivatives. We're going to learn some more derivative rules, and we'll get into the antiderivatives more there. But if it comes up, it may come up in the homework or something, just briefly. So there it is. Okay. All right. Last thing, and then we'll start talking about the homework here a little bit, and let you possibly get started with it. Oops. We've been talking about, and we've thrown out the word continuous here a little bit. On our homework, last quiz, we talked about a little bit. All right, so I want to get a little more specific with this, because this is something that will be on the quiz. All right, is what is a continuous function? We haven't had enough knowledge to really talk about it specifically, but now that we've done limits, we do, and we can talk about it. All right, so I'm going to give you two things. The informal version first. A function is continuous if it has no holes, breaks, or jumps. And in parentheses, I'll also add this. Or if you don't have to lift your pencil. Now, I'm saying that, but now remember, this is very informal. This is not going to be an acceptable answer, kind of like if we're talking about limits, I don't want you to talk about the dyno and the cars meter. I want you to say the y values are approaching this, whatever. Okay, but it's a good way for you to remember it and to think about it. So, a function's continuous has no holes, breaks, jumps, or if you don't have to lift your pencil. That's just kind of a generic kind of guide, but it's not mathematically very specific. This graph down here definitely is not continuous, right? It's got all three of these things. Well, I would call this a break right here. I would call this a hole right here. I would call this a jump right here. You might call it a break, I guess. Whatever, but that's what I mean. It's very informal language. This graph is not continuous. Continuous means nice and smooth, never have to lift your pencil, that kind of thing. No asymptotes, no vertical asymptotes, right? That would be a problem too. Now, I want to give you the formal definition. This is what you have to know and memorize. Okay? A function f is continuous at x equals a if, and there's going to be three things. Now this is actually in your book on page 106, I believe. we actually skipped it in section 2.3. Yeah, it's on page 106 in your book. Now, they do it a little differently. They list 3 things that makes a function discontinuous. Discontinuous means it's not continuous. Okay? They list the 3 ways that it's discontinuous. I'm going to write them in the positive version, what makes it continuous. All right. First of all, f of a must be defined. What does that mean, that it must be defined? There's no undefined point. It means it must have an output at that point. We're talking about at some point A. Now, a function is continuous if it's continuous everywhere in its domain, right? If it's continuous everywhere. Not in its domain, but everywhere. So if there's any place it's discontinuous, we say the function is discontinuous. Now, you can talk about an interval, like this graph right here is continuous, like in between here, and it's continuous in between here. You know, there's some places, some intervals where it's continuous, but the whole function itself, not continuous, discontinuous. All right, now, which one of these places here does this one fail? Which one of these places is this function not defined? Oh, whoops, I should have said must be defined. Sorry, I left out a word. F of a must be defined. Where is that not true here? At 1. But everywhere else it is defined, right? Everywhere else the function is defined. Oh, not at -1 either, I guess, right? Not at -1. But here, it's defined, has an output, but there's clearly a problem there. Here it has an output, there's clearly a problem there. It's not continuous those places. But, so this is not enough, we can tell. All right, here's the second thing. The limit, as x approaches a, of f of x, must exist. Now, is there any places on this graph where that fails? At 0. The cars don't meet, right? The limit doesn't exist, the cars don't meet. At 0. What about at 2? There is a limit there, right? There is a limit here. Now clearly, you'd have to lift your pencil here. This is not a continuous point. Continuous, again, nice, smooth, everything's fine. This is not continuous here. But it hasn't failed either one of these two. The function is defined, it has an output, and the limit does exist. Right? So neither one of those has been enough to show why that's discontinuous. Here's the last one. The limit, as x approaches a, must equal of f of x. The limit of f of x as x approaches a must equal f of a. The limit has to equal the output. In other words, the cars have to meet where the diner is. So here the limit's down here at 0. The output's up here at 2. They're not equal, so therefore it's discontinuous. So, have to have an output, have to have a limit, and those two have to be the same. If you have those 3 things, then you're going to have a nice smooth curve. All right, what I may give you is a graph like this on the quiz, and I'll say list the places where it's discontinuous. So you'd say at x equals -1, and at x equals 0, and at x equals 1, and at x equals 2. Now I may also ask, why is it discontinuous there? And I want you to give these reasons. I don't want you to say because there's a hole or because there's a break. I want you to say at -1, it's because the function's not defined. At 0, it's because the limit doesn't exist. At 1, it's because the function's not defined. At 2, it's because the last one, the limit doesn't equal the output. Okay? So you need to know those 3. I'm not going to make you recite them, but you're going to have to maybe give those as reasons in a problem. Okay, let's talk about your homework now. And you can get started on it. What time is it? Oh, wow. You got time. That's good. Must have skipped something. I just talked really fast. Let's look at your worksheet. Okay, back side of your worksheet is part of the homework. All right, we've already done a little bit of this in one of your homework problems. We did it last week. It was the one that had the delta x in it. It was like number 35. on one of the assignments. So this says each of the following limit problems represents f prime of a for some function f of x and some input a. Identify f of x and a, then use your calculator to estimate f prime of a, meaning use a table, because these are limits. So we're looking at this. Now I want you to think about this like the problem we just did. The problem we just got done doing right here. If you look at that worksheet, now take a peek at it, look at those limits on that worksheet. Don't they all look like this one here? They have like that 4 plus h, 2 plus h, 3 plus h kind of thing going on in them. Every one of those limits on that page are not just ordinary limits like your other worksheets have been. They're these special derivative worksheets, or limits, excuse me. So now let's look at this. Problem 34 that you had a while back, just like these directions, say what function where did this come from? Well, remember what we said? We said, how did this 4 plus h get here? We said f of 4 plus h. What's that mean? It means take 4 plus h and plug it in for the x. So this 4 plus h must have been where the x was. So what is this function? Oh, cosine x, right? Remember that? That's where. So it's like working backwards. So where did this limit come from? It came from the function cosine x. What was the a value we were doing the derivative at? The 4, the a plus h. Okay? So on your worksheet here, we're talking about, for this particular function, what was the function? What must it have been? What was the function? 2 raised to the x power, right? Because you're looking right there at the 3 plus h. The 3 plus h is in place of the x, because that's what we do when we do these f of a plus h problems. We take the a plus h and we stick it in for the x, so we're doing the reverse. Take the a plus h out and stick the x back in. So this must have been 2 to the x. What derivative are we doing? F prime of, what's my a value? That 3 right there. Okay? But now, to do this problem, you are going to take this red function here. Well, whoops, not the limit. Let me put it in blue. You're going to take this blue thing now to find this value, because there's no algebra I can do to this, like we did on our first worksheet yesterday. We're going to take this and go to our calculator, right? Like we just did a second ago. You're going to go to your calculator and you're going to put this in, the blue part. Not the limit part. Don't do the limit. Don't put that in there. Just the blue part. Except you're not going to use h, you're going to use x. And you're going to put that in, and you're going to look at your table. And you're going to jot your table down over here. Go ahead and do it. We'll check our answer. What do you get? Are we there yet? Too big enough. How much? That doesn't sound right. I think it's 5 point. Make sure you don't have an H there. Make sure they're X's. I think it's 5.545 or 44. 4445. Either one, if it rounds or it truncates, that's okay. And what does that mean? What does that mean? That's that number that has 2 meanings, kind of like the $100 in my pocket or the 100 you're going to get on your test. That means the slope of this red function at 3, but it also means the limit of this blue function as x is getting close to 0. But that's the answer we're looking for. There's your table. But this limit was represented of this function, and that's what you do on all of the rest of that page. Now, some of you on your homework, I've come around, and you didn't do it in here, but in their class, somebody said, oh, there was a book problem, right? There was a book problem? Yeah, okay, so there's, on your sheet here, so just to make sure everybody's with me here, right? It's this group of 3 right here. We got a few problems in section 2, 3. We got a few problems in section 2.4, and then this last bit of this worksheet. Okay? So it's those three things right there. All right? Did you get it, Josh? Oh, right. Oh, yeah, good point. Because the limit is as h approaches 0, right? So yes, every one of those will go at 0. And then, oh, is that where we're going? Like that? Yeah, okay. Oh, good. We got done perfect. Yeah. Okay.